Hi everyone. Hope you're doing well. So I want to remind us to keep staying safe during this COVID-19 period. Okay, today I'll be taking the master class in convolutional neural networks. We'll be discussing how convolutional neural networks works, the principles, the operations, how and their applications to different kind of things. But before we dive in, I'll talk about Data Science Nigeria. Data Science Nigeria is a non-profit organization driven by a vision to build a world-class artificial intelligence knowledge, research, and innovation ecosystem that delivers high-impact research, business use application, locally relevant AI-first startups, and thereby increasing employability and drive for social good use cases. And our convener is Dr. Bayo Adekombe, who is a Chief Transformation Officer at MTN Nigeria. You can visit us at our website, www.datasciencenigeria.org. Okay, about me, I'm Stevoni, data scientist and researcher at Data Science Nigeria. And you can reach me out on Twitter at Steve Oni. So let's dive in into this course, convolutional neural networks, or you can pardon me to call it ConvNet. In this course, we'll be talking about how convolutional neural network, as I said earlier, before convolutional neural networks, what is ConvNet, how it works, intro to image classification, and intro to transfer learning. Before ConvNet, there have been different attempts in which people are using to detect objects in an image or what an image is all about. One of the attempts is trying to find out the edges that an object has in an image. For example, look at this cat over here. So from cat, you can know that okay, these edges around the ears. So if the system can be able to discover these edges here, so it can be able to know that okay, that this is a cat. The way this principle work is, according to physics, we are able to see objects through the reflections of light, through them, bouncing through the edges of those objects. So every object has an edge. So they all have edges. Humans also have the edges. What this SPA system does is, once you pass this image into this system, the system look for those features, or is it the features of humans, the features of cats, the features of dogs, the features of house, cars. So from there, it can be able to detect okay, if it contain this kind of edges, if it contain this kind of features, then is a car, is an human, all those kind of a thing. But this expert system has their own flaws because you can't just detect what an image is, or what an object, the object is, just by the edges. So there are more things you need to consider. And one of the flaws of an expert system is occlusion. For example, we can't discover any edge here, but the edges of this cat are not showing. Maybe the ears, the nose, the claws, they are not showing. But the expert system will have difficulties in predicting what kind of object is present in this image, and also here just a tail. So we can't be that sure that this tail is for the cat, because it can't detect the edges of cat in it. And also deformation. Sometimes the way the edges of an object is being shown in an image, can make it look as if it's an other object, but actually is not that. So this kind of way, an expert system will be very confused on what kind of object is present in this image. In the year 1998, Yalekun discovered convolutional neural networks, which is used for digits classification. But over that period, people were not using it that much because of the computational power, and it requires lots of data. So in 2012, we have lots of data from ImageNet, and the computational power has improved. So so they were able to use ConvNet to win the ImageNet competition. So earlier, before I discussed about these flaws of an expert system, there are lots of flaws in an expert system apart from these two flaws I just showed you here. So, what's the approach of convolutional neural networks? So, how the convolutional neural network work is that instead of trying to add code the features the system should expect from an image, we can just define some parametrics function. And what this parametric function does is it does not contain any prior knowledge of what the image is. What it just does is just some random variables, and we train on those random variables. We update them as time goes on while training the image, and this function gets to learn the patterns in the images. So it gets to learn the patterns. If you train it with that of cat, it gets to learn the patterns that in this that make a cat, and that makes a house, a car. So it learns this function learns the whole pattern in this image using this parameter or weight. So I'll be discussing how this work. Okay. So some of the applications of ConvNet is object detection, detecting what an object is. They are not just the ConvNet is not just using an image to detect if the edges of the object to detect if this is a car. There are some features it has learned to make a car, as I discussed earlier, using the parametric weight, and this image captioning. Also this to detect what kind of event is going on, detect the person is on a bike. So this action classification. So what's the intuition behind ConvNet operation? ConvNet, as I said earlier, is used for different kind of thing. In fact, we use it for language models, for neural machine translation. Maybe you want to translate from English into Yoruba or to your native language. We use ConvNet also to do that. So this ConvNet is very important to our understanding of deep learning because of how it is being used in most applications of deep learning, in most operations of deep learning. So understanding ConvNet and how it works will aid our ability to understand some concepts in deep learning. It will also solidify how things work. Okay. So before we dive into this convolutional arithmetics, and this is the math behind convolution. So let's get to see the code. Okay. This the code for CNN. Just to get the basic intuition of what convolutional neural network is. So here, what this notebook is actually doing is we are trying to look at how the convolutional neural networks work, how the kind of operations is using. So what actually is not all of us that know how to code right or very good with code, and I believe sometimes the best way to explain things is through visualizations of what that thing is. So what this notebook is actually doing, we're taking this image here. This is how the computer sees an image. It does not see it like an actual image. It sees the image as a matrix. So here, so I'll be explaining all this first of all through visualization, trying to sketch out the principles of how content works. Okay, instead of starting with this code, let's try to use notes. Okay, I will describe the operation of the notebooks, the CNN notebook here. CNN notebook here. What this notebook is trying to do, I want to explain it with this Microsoft Note. So first of all, what this is doing is we're taking this image, yeah, this shoe image that I'm showing here, this shoe image. This is it. So the computer will not actually see this kind of image. It's not actually seeing the image itself. as I said earlier, it's seeing the matrix of that image. So the first thing we do is pass this image. So let me use this. So the first thing is that pass this image. So this image, we pass it through a function that converts it into a matrix. So what it does is convert this image to something like this. Don't mind my drawing. So it converts it to something like this. So what this means is that let's say this image here is 1000 by 1000. Let's say 100. Okay, 1000 by 1000. So what this function here does is it resizes the image to this format. So an image is like it contains the width, the height, and the channel. What I mean by the channel is the RGB. So it contains three channels. So please don't mind my drawing, just for us to understand. Okay, this is three channel. We call it also the depth of the image. So it's 3 here, and it also contains the height. Okay, let's say this is the height, and the height is let's say 224. This is 224, and we also add the width. So we have the width. So this image is being resized from 1000 by 1000 to 224 by 224, and the channel is still retained. Remember, this channel is the RGB. We call it the red, the green, and the blue. Those are what forms the colors in an image. So now, once we've have this already, you get. So what it does is we need to pass this into the coordinate. So now we can pass this into the coordinate, because this is already from this image we convert it to what the computer can see now. So now in passing to the coordinate, that is the function we have. So let's say this is the function now. So this is the image here. This is the image here, which is the x. Which now we want to define our weight here. So as I said earlier, coordinate is using a parametric approach. Is using a parametric approach. So we have to define this weight, and these weights are just random number. They are just random variables that is being trained. Sorry. Sorry. So these weights are being trained. So as you are training the coordinate, the weights are being updated as time goes on. So now we can define our weight. Let's say now for this image you want to use a weight of 3 by 3. So this is a 3 by 3 grid. Now what the component will actually be doing is taking this 3 by 3 grid and converting it with this image here, and converting it to this image here. I hope we are getting it. So this is the image here. This is the matrix we ourselves will be defining. Okay, so now let me go back to the code and show you. So now we call this image with this function here, and we try to resize it with 24 by 24, so we are able to see it here. So this function, to by tensor, it converts the image it converts from the image to the matrix in which the computer can see by itself. So as I said earlier, I said that this image contains something like this. Okay, let's say this image is okay, Okay, we've already resized the image here to 224 by 224 by 3 by 3. But actually our when we are trying to use it with the CNN, or rather I call it ConvNet. Yeah, if you want to use it with the ConvNet layer in PyTorch, PyTorch does not take the image like this. So we still need to go a process of making the image, turning the image to something like this. 3 by 224 by 224. So this is what we call transpose. This is what we call transpose. So this is what the covenant will be saying. So remember I said the computer is saying the image as a matrix. So this matrix from with all the numbers ranging from 0 to 255. And for we to also use it with the convnet layer, we have to normalize everything here. So we normalize the weight, so it ranges from 0 to 1. So how do we normalize? So we divide all the values in the matrix by 255. So if you divide these values by 255, so they'll be ranging between 0 to 1, because 255 is the highest and 0 is the lowest value. So I did not talk about this permit. So what does permit actually means? So as I said earlier, let's say this is the shape of the image. Let's say this is the shape of the image. So the image contains the height. The height is 224. The width is 224, and the channel, that is the RGB, that is the color RGB. Remember, so that is 3. So if we print it out, it says shape 0. In order to access the index, say shape 1, and we say shape 2. Get? So now what this is what this is giving us, 224 by 3. So for us to transpose it, we are using permutes because we are having different axes, so we want to transpose it now. So these are the axes: the first axis, the second axis, the third axis. So the RGB channel is in the third axis here. The width is in the second axis, and the height is in the first axis. So for it to reshape it to what the covenant layer can see, so we just do shape, bring the third axis forward, and bring the first axis, make it to be the second axis now, then shape 1. So if you see, it's giving us 3 2 4 2 4. So that's what this permit is actually doing. So after that, we convert the image to float, as I said earlier. Convert the image to float. We also, here for us to pass it through the covenant layer. We this is an image now. This is the matrix. So the matrix is just from one image. So what the covenant takes is a batch of images. You get a batch of images. As this is, we cannot have, let's say, this whole body here. Times 36. So it can be times 36. That means 36 batches will be passing through the covenant layer per epoch, that is per time. Now, so before I go back to the notebook, as I said earlier, the covenant is taking images, which is by batch. So let's just look at let's have a simple, let's just take the first channel of the image. Let's take the first channel. Right, I said it has 3 channel, or you can call it depth of the image. Now let's take the first channel of the image. This is 2 to 4. Let's say this 2 to 4 by 2 to 4. You get this 2 to 4 by 2 to 4. But let's neglect the dimension. Let's just give it some certain grid. Let's say a grid of let's say 7. I guess it's 7, yeah. Let's give it a grid of 7. So we are dividing the image into grids. Okay, let's make it 6. Okay, let's do 6. 1, 2, 3, 4. Okay, this 1, 2, 3, 4, 5, 6. So this is a 6 by 6 grid. So let's just think of the 6 by 6 grid as a 2 to 4 by 2 to 4 image shape. Now, what the company does is multiply this by this. Okay, we have this, we call it the kernel size. So the kernel size is the dimension of this shape. Let's say this 3 by 3. Okay, let's say this 3 by 3 now. So this is the kernel size, which is 3. And we can now say, okay, how many kernel size, how many kernels you want to use, or we also call them filters. So how many filters do you want to use? Let's say you want to use also 3 by 3 filters. Let's say 3 by 3 filters. So we have 3 of these. Okay, we have 3 of these, right? So now what this does is each of these filters looks at this image, looks as the same size of these filters. It looks at it also in the image. I hope you understand what I'm trying to say. So it looks at them in the image across the depth. Okay, this is what I mean. So this first convolve with this image here. So this is how it is for this first filter. So far the filter size is 3 by 3. So we first take 3 by 3 layer here. Let me change this. So we'll take the 3 by 3 here. Get so now what this is doing is there's something we call matrix multiplication. Yeah, matrix multiplication. So what this does is this first this first filter, this is a random filter, we generate it randomly. So they have random values, they have random values. So what this does is we do the matrix multiplication with this with some parts, with some local regions in the image, which is also a 3 by 3 part. So this now we do a matrix multiplication with it. So I'm still going to explain how the matrix multiplication works. So I will also have what we call stride. We have what we call stride here. So what stride actually means is how we move across the image. Yeah, let's say now after let's say after doing the first matrix multiplication with this first side of the 3 by 3 in that image, so then it moves again. Let's say we are using a stride of 1. Let's use a stride of 1. That means take a step of 1 to the right. See, it does this. Can you see it? So it does this. Okay, that is a stride to the right. So now it goes again, it does this the matrix multiplication with this one also. Then it comes again. Okay, another stride again. So it's taking those steps one by one. So it's taking the steps one by one. So it does the matrix multiplication with this. So now our output also, okay, now what this does is, as it's doing this the matrix multiplication through the first side, let's say the output of this channel will also be giving us this with this same kernel size here. So it does this with this. So the matrix multiplication with this and this will give us a single value. We put a single value here, we put that single value here. As we move to this other side, we put the single values here. As we move to this other side, we put the single values here. So now again it comes down again. Okay, let's say a stride after it has reached the end of this matrix here, then it comes down to this side here, takes a 3 by 3 matrix. So it does the matrix multiplication. So it does this it does this with the image, and we get so as it's doing this, we are getting the matrix multiplication. So let's go back to the code. So this is what I mean by that. So this nn-conv2d, so it's taking the what nn-conv2d first does is conv2d. So conv2d takes in the channel of the image, then it takes in the output channel, takes in the output channel, and we define the kernel size. As I said earlier, we define the kernel size, and we also give it padding. So what does padding stands for? So if we come back to this side, let's say after moving through this image, now is the image still have some steps to take, then it comes like this. You see, there's no image here, right? No, the image stops, the image width stops here, but there's no image here. So it will be giving us the output to be giving us so I will still tell you how to calculate the output of a component layer. So once it gets to this side, what it gives us is a decimal value. So we don't want a decimal value, we want a whole digit as the width, as the height, and the channel. So so what padding does is we add okay, so we pad this image with zeros across, let's say, sorry for the, so we pad this image with zeros here. So we just draw this forward, so they are filled with zeros. So here all these sides are additional matrix height and width. So but they are all filled with zero. So padding helps us to, if we pass in 224 by 224 into the current, instead of, let's say, bringing out 112 by 112, so it still brings out that same 224. So this helps us to this helps the component to train deeply, like you can have a very large depth of component, the conv layer 1 to conv layer, let's say 53. So as time goes on, we don't want to keep reducing the width and the height of the image. So so now we don't lose the information that the image contains. So we pad the image to still retain that same features in the image, to still retain the image size. So what this does is, so now we use, so what I'm trying to experiment here is to tell you that ConvNet is also just like we can use it for the Sobel algorithm I discussed earlier, in which I was saying we pass the image, the cat image here. So this image here, you can use Sobel filter wish to detect the edges, you can detect the horizontal edges and the vertical edges. So what this does is the vertical edge detector, the horizontal edge detector, and the normal conv detector. We just use the random variables. So this is the weight I'm talking about. The weight I'm talking about. So it's this is the weight here, 3 by 3, across the depth of the image, and this is the depth of the filters itself. So we have 3 filters. So this is 3 filters across the depth of the image, and this is the height. So now I'll be using this Sobel filter algorithm to show you that conv layer also can also detect edges in image. You can use convnet layers as a Sobel for Sobel algorithms. Okay, now remember I said earlier that we fill this weight here, they are just random variables, so we don't know what it is. We just take a uniform random variables. So so as time goes on, as we train them, they are being updated. Now let's think of the weight as being updated to discover horizontal edge in an image, and also to discover a vertical edge in an image. So this is the you can check online for horizontal edge weight. So this is the weight, or we call this the kernel for horizontal edge detector, and this is also the kernel for vertical edge detectors. So this is the matrix. So you can search online for it. So now, instead of defining a random weight for the ConvNet layer, we are using this H kernel, that is the horizontal kernel, and the vertical kernel for the weight. So now what this side does is, across the whole dimension of the weight, this is across 3 by 3 by 3, you know, the shape of this horizontal edge weight is 3 by 3. So it's 3 by 3. As you see, it has three elements here, and the matrix itself also contains 3 vectors. So this is it. So we fill the the horizontal curve net layer weight with the H kernel, and fill the vertical conv layer with the vertical kernel. So now we pass in the image into this horizontal conv and the vertical curve image and the random weight conv. So you can check the feature map or what it is. The feature map means the output of the convnet. So what I mean is, after doing this, so there is an output. So there is an output, and that output is also this image. Is also this image. So the output is also this image, which is what, 224 by 224, 224 by 224, which has passed through convolutional neural networks. So it's during the matrix multiplication. So this, after this matrix has react with this image, we will surely have an output also. So so those output is also 3 by 224 by 224. So so likewise, if so the depth of this output now, depth of this output is still determined by the dimension of this of the kernel size you use. So it depends on the dimension of the kernel size you use. So let's say here we are using 10. So the dimension of the image will be that will be 224. That will be 224 by 224 by 10. So that will be the dimension of that image. So now after doing this, the h map, that is the feature map. So we call the output of a conv layer, we call it feature map. So the feature map, which is 3, 224, 224. So now we want to see what this feature map actually contains. We want to see what we want to convert it to image so that we can visualize it. We can actually visualize the tensor itself, which is 3224 by 224. So as I said earlier, images, the normal dimension for the image is height, width, and the channel. And here the what the conv layer is outputting is the channel, is the height, and the width. So we use permute to change, as I said earlier here. So we use the permit to change it back again to 224 by 3 in order for us to visualize it. So we do this. So far is a component layer, it contains the gradient. So we detach the gradient or the feature map from the image and convert it to numpy in order for us to visualize it with matplotlib. So now for the horizontal edge detector, we're able to have this. So this showing the horizontal edges in the image. So the horizontal edges, and okay, we can see it clearly here. So that is for the horizontal edge. And also for the vertical edge detection, so we use, so from this from here, so you're able to see this horizontal edge detection here. So this is the horizontal, this is the vertical edge detection. You see these lines are breaking, it's showing these lines in the vertical side. So now for the random weight, we declare three component layer: the vertical component layer, the horizontal component layer, and the random weight component layer. For the random one, it does not detect anything, so they are just random. So now let's see what this random weight is all about. What are they actually saying? You get. So now we make the weights to be between, we normalize them to be between 0 and 1. Yeah, we normalize them to be between 0 and 1. So we subtract by the mean, we subtract the theta by the mean and divide by the difference between the maximum numbers and the minimum number. So we pass it through this loop to see what the random theta is all about. You see this and this, so they're just detecting random stuffs. And normally the kernel, the horizontal kernel also have this kind of shape. So the horizontal kernel normally should be like this. Okay, still loading. Okay, still loading. Let me use this. Okay. So for the horizontal kernel, so it's something like this. We have this, we have this, we have this, we have this. Okay, let me use this. So this is being painted black, and this is black. That means the text. So this is how the weight is. And for the vertical kernel, this is how it is. So then this place is painted black. So this black here, black. So this black here. So this is for the horizontal, to discover the horizontal edges. this to find the vertical edges. But here you see that this contains black, contains shade of a lighter shade of black. Contains a more lighter shade of blacks, contains white. So unlike this that just contain blacks throughout here, blacks, white, blacks here. So this is just discovering different random patterns in the image. So that is actually how the ConvNet works. So let me come back again. What it does is we create the weight, the weight of the ConvNet layer, and we take our image. So we convert this image with the weight. So each of these weights is looking at a particular region in that image. So this is looking at this region in this image, and the region they do look at, we call it receptive field. So this receptive field, so this image looking at this particular space in this way, looking at this particular space in this image. So this side here, we call it the receptive field. So it does the matrix multiplication with this receptive field, then it move a stride to the right. So after completing the stride to the right, then move a stride downward. So that is how it does that for every of the region in the image. So when training ConvNet, we have the lower layer and the upper layer. When I said the ConvNet layer 1 to the last ConvNet layer, so each of these layer capture different features. So the first layer captures abstract features. So I'll still discuss how I'll still show you how that means. Okay, let's say this is the abstract features here, where this arrow is. So the abstract features like colors, patterns, and just the color patterns. So as we move deeper into the layers, so it begins to detect more concrete patterns like this. Like this is a circle. I can say this is for detecting eyes. So that's how ConvNet is. So that is ConvNet operations. And we also have the pooling layers. So as I said earlier, when we pass the image, we have ConvNet layer actually. So the first layer to the last layer, we pass the image through these layers. So as we pass the image through the layer, if you are using padding, you can keep padding them. So the output, the input to the so the ConvNet also have the same output dimension with that of the input. Let's say you pass in 224 by 224 by 3. So the output will also be 224 by 224. Then depending on the numbers of filters you are using, let's say you are using 64 filters, so the output will be 224 by 224 by 64. You get? So now, so you do that same throughout, but the sometimes the parameters, sometimes when training this ConvNet layer, the computational power is somewhat heavy. So we do use the max layer to reduce the parametric, to reduce the spatial size of the ConvNet. So what this does is, when we pass in this image here to the pooling layer, it reduces by 112. It uses to 112 by 112 by 64. So 112 by 112 by 64. So what this max layer does is, using that same patterns here. Let me see if this is still loading. Okay. Using that same pattern, let's say you have something like this. Let me see that. Okay, let's use this for okay. Let's say this 3 by 3. You get? Okay, and we have this bit here. Let's say we are using 2 by 2. Okay, let's say we are using 2 by 2. We are using 2 by 2 here. Oh, I said 2 by 2. Okay, let's say we are using 2 by 2. So we are using 2 by 2. So what this image does is, so as I said earlier, we do the matrix multiplication with this. So instead of doing a matrix multiplication with this, So this is just like a lookup. So once you put this image, it looks for that same 2 by 2 dimensions to that image. It looks to the 2 by 2. So it takes the maximum number here. We have 1, we have 2, we have 3, and we have 4. So now we have 1, 2, 3, 4. So passing this pooling layer, which is 2 by 2, passing this pooling layer to this, we just, okay, what's the maximum number? We call the max pool layer. So this is the max pool layer. It takes the maximum number here, which is what? Which is 4. I hope we are getting it. So it takes the maximum number, which is 4. And for this image here, we have 1, 1, 5, 6. It takes the maximum number, which is 6. Then it move. So here I'm using a stride of 2. So what this max pool layer takes, this max pool layer takes 2, which is the kernel size, comma the stride. So this is the kernel size, which is 2 by 2, and this is stride, which is move 2 steps. That means take 2 steps. So if you come back to this, so after doing this, instead of the former process we are using in the CNN, instead of just coming to this side, it takes 2 steps. 1, 2. 1, 2. Then it starts from here again. So it starts from here again. So what it does here is take also the maximum number here. Let's say 8 is the maximum number, or let's say 9 is the maximum number here. 8 is here, 5 is here, and 6 is here. So it takes in this maximum number of 9, then it outputs this 9. It gets. So that is how it works here. So it uses the spatial size of this image into a 1, 3, 2, 2, 4. Yeah, it's uses to 1, 2, 2, 2, 4. But we are using padding. Yeah, we also use padding in pulling layer. Yeah. So use the pattern of 1. So if you have it will bring out the same shape, which is 2, 2, 4. Oh, sorry for saying that. We do not use padding. So it uses this image. It uses this feature map. This is the feature map from the CNN. So this is the 224 by 224. We pass in this feature map into this pooling layer. So I will take the first index. What do I mean by index? Remember, this image is 1, 3, 2, 2, 4, 2, 2, 4. So instead of taking, so the first, and I said this thing stands for batches. That is batch of image. We have just one batch here. So we just take the first batch, which is, so taking the first batch will give us this output shape 3, 2, 2, 4, 2, 2, 4. So this 3, 2, 2, 4, we pass it to this pooling layer. So and we permute. So for us to convert it to image again, we do the same thing as we do here. Where is it? Okay, here. So convert it to the image. So we convert it to the image, then pass it to the MLT show. So you see, it's not actually doing anything much. This is the horizontal features. It just using the spatial size of the CNN output. Now, okay, that is all about the ConvNet layer. So let's go back to our slide. Let's talk about the convolutional arithmetics. So this is the convolutional arithmetics. Okay, this is the convolutional arithmetics. We take in this. So now what this does, so I want to explain the how the matrix multiplication works. Now, as I said earlier, this is our kernel size. This is our kernel size, and this is the convolutional this is the convolutional, let's say this is the image. Yeah, this is the image width, and this is the image height. So now we have 332 001 312. Get. So we are trying to do matrix multiplication with this part. So what the matrix multiplication is all about is, okay, let's say for the kernel we have, for the kernel the first one we have 0 0 1 2, we have 0 1 2 2 2 0 0 1 2 0 1 2 2 2 0 0 1 2, if I'm right. Okay, that is it. So now we want to multiply it. So what this does is we are multiplying it. We'll multiply by this digit here also, which is 332 001 312. So 332 001 312. So we take it here, 3 3 2 times 0 1 2, then 3 1 2 times 3 1 2. Okay, we're having 16. So let's see, maybe it's correct. 0 times 3, let's see, 332, yeah, 001 312 332. Okay, this 2, 332 0, okay, 001. Okay, this is 12. So you see, so we've done the first matrix multiplication with this. So 0 1 2 2 2 0 0 1 2. So we multiply it, we do the matrix multiplication with 3 3 2 0 0 1 2 3 1 2. So if you see, the kernel is now 12.0. The kernel is now what? 12.0. So it's also move another stride. You take one stride there, you get, it takes the one stride there, so it's multiply with this also. We're having 12.0 12.0 7.0. So that is the basic matrix multiplication. That is the basic matrix multiplication of how convolutional neural network works. So it does that to update it, then it concatenates all these kernel shards into this image shape back. So this is how it works. So now we're able to get, so that's how the kernels are being updated. So now if we are using padding, so if we are using padding, we pad it with 0. So this pattern, as I said earlier, is just to retain the same dimension of the of the input. So if it's the same spatial dimension, which is 224 by 224, so once we pass this to it, we still retain that 224 by 224. So now let's go to the CNN training. So I'm using PyTorch. So what we do here is, now we are trying to train an image on train the components with images. So what I did is, I searched online for let's say shoes. Let's say we want to train it on shoes. So this is Google image. So we take, so these are shoes, Adidas shoes. So we have a Chrome extension which is called Zip. So this Zip, we download all the images in this page. So that what we use to download the images here. The images we use for the training. So so you can see them here. Let me show you. Okay, so now, this is the training side. So this is the training side. So this is the training folder. So it contains the Adidas. So these are the Adidas, and it contains the Brook shoe, and it contains the Nike. So it contains the Nike. So we'll be using that to train. So we'll be using that to train our component layer. So before we do that, let's just see how the basics of how it works. So there is this JavaScript interface that was JavaScript for components that was designed by Andrej Karpathy. So let's use that to just see how the component works before we train it. So now I'm going to drag a truck in. Let's see this image. Okay, let's say we wanted to predict this, the truck. Okay, we run this predict. Okay, so it's able to predict the truck. So what this model does is it was trained on Cipher 10 dataset, which contain trucks, dogs, ships, cars, airplane. So it was trained on it. So now you just want to see how the covenant works. So it's able to predict, okay, the highest probability is truck, followed by dog, followed by sheep. So now let's see the layers in the covenant. So this is what I was talking about. So the input dimension is 32 by 32 by 3. So this is it here. We pass it through this conv layer. So this is like what it's saying. It's saying this random weight. So this is the weight. So I said it's saying some abstract features, and this is like the output, the let's say the activations of the component. So you see, it's just like edge detectors trying to discover edges in it. So now the components. So after component, you use ReLU. So ReLU is used to drop the weight sometimes in the image gradient, the image weight and the image gradient. We do have some values that are zeros, that are below zeros. So what ReLU does is clip these values to be from 0 to the maximum number in the weight. So this helps prevent gradient explosion. The numbers should explode. So and it helps sometimes the weight update can get stuck. If the values are below 0, it can get stuck. So you just have to clip it to be from 0 to the maximum values. And we have this pooling layer, which reduces the spatial size of from 32. It reduces to 16. Then from the pooling layer, we pass it back into the component layer, which is now 16 by 20. Do the same thing, ReLU, pass it through pooling layer again. So from the pooling layer, we take in the output of the pooling layer, we put it back into this component layer. So you have this ReLU also. This is the pooling layer. So this is the pooling layer, the last pooling layer. Then we pass it into a normal neural networks. We use our softmax output, which predicts. There are 10 classes in the. We have 10 classes in the image. So these are the 10 classes. So it predicts the probability for each of the 10 classes. So that is all about that. So let's come back to our code. So don't let me bore you much with the code. So what this does is the train transform. As I said earlier, we resize the image. So your training image might contains different spatial dimensions. It might be having 1000 by 180, 180 by 300, different, but we want them to be the same size. We want them to be the same size in order to increase our computational speed, and the GPU does not take different random dimensions, spatial dimension. So from here we resize it to 255. Then we transform, we crop it to 224. Then from 224 we convert it to the tensor, and we do our normalization just similar to what I did earlier by dividing by 255, yeah, 255, which is the maximum number. All right, yeah, we divide it by 255, which is the maximum number. So the values will range between zeros and one. So so these are the process of calling your image from the folder. We use the train, so we call this from the train folder, the image from the train folder, and we apply this transform to it, and we call the test data from the validation folder, and we apply the transform to it. And so far we now have our validation set, so I'm using a subset sampler. So we can use a subset sampler from PyTorch data sampler. So what we do is, instead of instead of just training just with the training set, we want to validate the performances of the ConvNet model. So we check for the range of the training set. We take the list. I will get the percentage of the validation set we want, or of the validation size we want, which is 0.1, about 10% of it. So we shuffle the index. So I'll create a subset sampler here. So from the subset sampler, we can gain our training in DL and validation DL. This is a data loader. So this helps us to create the bash I was talking about. So the image here will be now. So the bash will be like, per each bash we'll be having 20 command 3 command 224 command 224. So this will be the bash. So this will be the bash for the training images. So here we can see the image here. These are the Brooks, and these are the Adidas and the Nike. So yeah, this is where we define our ConvNet layer. You see, we define it here, NN-conv2D. So we are taking the dimension, which is the channel of 3, and we're taking the output dimension will be 16, and we have the kernel size of 3, and the padding equals to 1. And I have the self conv2D. We have nn.conv2D. So the second one will be taking 16, which is the output from here, which is 16 dimension, 32. I have the 32 output. I have the 3 dimension and the padding. So the third one will also be taking that 32 output, taking the 32 output as input here, and also be outputting the 32 dimension and the 3 the kernel. So this is how it works. So this is how it's going to be. So let's say we have 20 by 3 by 224. Okay, let's say without now applying polling layer to it. So the next one will be 20 by 16 by 224 command 224. Then the next one will be 20 command 32 command 224 command 224. So this is how it is. So this is how it is being passed. So from the first conv to the second conv to the third conv. So now we have the pooling. So we are using pooling of kernel size of 2 with the stride of 2, and the adaptive average pooling of 1. So our fully connected layer, that is the first layer, we take in the inputs, the output from here. This output here, which is now 32, it contains 32. So we pass it through this and output and so we have this in the dimension of 500. So we have this in the dimension of 500. So we pass it through here. So here we have this 500 by 3. So this dimension will come out to 500, 3. So here we want to so far we have 3 classes. So the softmax output will just be 3 classes. That is the probability of the 3 classes across the 22 images. Remember I said we have 22 images. We have 20, 3. So this one with 20, this is the per this is the per image. So the probability will just be something like this. Let's say for the first image we have 1. That's the first. Let's say the first image is the 0 dimension, and we have the probability to be something like this. 0 0.1, 0 0.8, 0.1. So we see this is the probability. So softmax will make sure that the total width, the total probability should be equals to 1. So as you can see here, 0.8 is the maximum value. So that means it will be Nike. That means the class has the probability of being Nike. So this will pass the image. So in the forward, so we declare the forward. So while training, while training, we pass the image to the conv1, the frelu. As I said earlier, relu is used to clip the image between 0 and the maximum number. And apart from clipping the image from 0 to maximum number, so this convolutional network is a linear layer. Is a linear. We can think of it as a linear layer. So now, as a linear function, think of it as a linear function. So what it really does is it converts linear function to a non-linear function, because a non-linear function has the can fit well into any function. Okay, let's say we have this now. Let's say we have this function, let's say this function here, let's say something like a quadratic function. So what this does is, if we use a linear layer can just split this like this, which doesn't actually perfectly fit into this the distribution of this function. But we can have something like relu, which is a non-linear function. A non-linear function helps us to fit well, if not perfectly well, but it can fit well into this kind of function compared to a linear layer, a linear function. So that's what the frelu does. Is a non-linear function which convert this linear function into a non-linear function. So we do that for the first polling. So the second polling is adaptive polling. So what does adaptive polling does? Adaptive polling reduce. Okay, let's say after this year we have this. So what adaptive polling does is it perform a polling, an average polling. Then from the average polling we will be getting an output of 20, 32 by 1 by 1. So this will make it easier for us to flatten it. So then we flatten the image. So here we flatten the image. So we flatten the image. So we have to be 20. That will be 32 times 1 times 1. So we'll be having 20, 32. So we have 20,32. So that's what is being passed in here. So we pass it to the dropout layer. So what this dropout layer actually does is, so let's say these are our neural networks. We have the circle, we have the circle, we have the circle. So everything is trying to predict here. So this is the neural network is. This neural network. So let's say this is our hidden layer, and these are our inputs. We pass in this input. And this one is to detect one output. Let's say we have to detect one output. So what this does is, what dropout does is, there are some times that some layers do not actually participate in the in the detection of those image. So what it does is it drops some layers. It drops some some hidden neurons. It drops some neurons, pardon. So it can drop this while training, that means randomly, and in the next training step, it can use it, then drop this other one, then drop this, then drop this. So that's what dropout is all about. Just dropping some neurons in it. So I'll pass it through the the first layer, the first hidden layer. We use dropout, and we use the second hidden layer, activation. So we have the model show classifier. So now we initialize this model. We initialize the model, and we put it on GPU. So as you can see, this is conf 360 3,16. We have the kernel size of 3 by 3 and a stride of 1 by 1 with padding of 1 by 1. I have a mask 2D 2 2, padding of 0, dilation of 1. So we have the adaptive average pooling. I have the linear in features are the output features. I have the dropout of 0.25. The dropout is just as I said earlier, is to drop some neurons based on the probability if distribution. So and we also have the cross entropy loss. So while training the image, we have the loss. So the loss is to know how far away from the target, how far away from the target while training. So and we also have the optim SGD, so optimization function. So what optimization function actually does is, okay, while training we have this our training curve, the loss curve. So now while training now, we are trying to move from here to the maximum to the minimum loss. It gets coming from the maximum loss down to the minimum loss. So we are trying to get the lowest loss, get the lowest loss that will help us improve this image. So what optimization function does is, so it's try to move the gradient to the what to the steepest part to get the global maximum. So this is the global maximum here. So this is the graph. Let's say loss. You get, so we are moving from this. Let's say this is the 4.8 loss to this like 1.0. So it helps. So we're using the training to update the grade to update the gradient. So it moves it. So the step in which it takes in moving from this from this upper hill to the lowest hill, we call it learning rate. So you can use a learning rate of 0.1. That means it move if you are that's if you are doing the calculus. So I'll be going deep into that. So the learning rate is the step it takes in moving down the hill to the global minimum. So we train with this epochs of 5. So while training, our loss is very bad because I just declare some random architecture. So we declare some random architecture, the loss is very bad. So after training, we see that it performed well with Broke, but in the others, Adidas and Nike is not performing well at all. So just 41% out of all. So you see, it's just performing well with Brooks. So that is where so sometimes instead of declaring your own architecture, there's what we call transfer learning. So transfer learning helps to get transfer learning helps. Okay, we transfer. What transfer learning works is we've trained on a particular set of image sets. So instead of training from scratch again, you use what the models has learned from a particular data set. We can transfer it to our own data set. So this is what transfer learning is. We still use that same step we use in the former in this CNN notebook. So we get this transfer learning from model.resnet34, which is pre-trained. Now this This model ResNet 34 is using the image net that I discussed earlier from the image net dataset. So instead of using the output features from the image net, our own numbers of class is three. So ComNet has the feature layer and the let's say the classification layers. So what we do is we change the last layer of the pretend models to fit into our numbers of class. So what we do is we get the model.fc. As you can see, this fc. Okay, I now print it out. Okay, this fc. So we get the fc and we get the features in that fc. So we get the features. So we change it from the previous features into the previous output into our own output, which we want the output to be 3. Then we also use the same process, nn cross entropy, and we use the optimization function. So after using this optimization function, so we see, because this model has trained before on different data set, image net contains dogs, cats, humans, different type of images. So this enables our us to get a better performance. So we have this validation loss compared to this one. Compared to this that was giving us 1.1. So this is giving us from 0.5 to 0.221037. So we have this pill. So after training we can test. So let's try to test. Let's check the accuracy. So compared to this, we have 100% accuracy for the Brook, we have 79 for Nike, and you have 90% accuracy for Adidas. So in total you have 91% accuracy. So you can see it was able to predict well for the Brook. It's actually having fault with this Adidas and Nike, differentiating between Adidas and Nike. So you have the Brook, we have the Adidas, and the Nike. Yeah? So that is the full details of how convolutional neural networks work. Don't forget, convolutional neural networks takes this kernel width, it update them during this process of training. So during the process of training, we use this we call it stochastic gradient descent. So that was we used to train. We used to update it. So we use that to update, and this cross entropy loss is used to find out, okay, how what's the difference, how close are we to our target, which is the label. How close are we to the label of the original image? So I think that is all with ConvNet. So now I forgot to talk about calculating the output shape of ConvNet. Calculating the output shape. How would the output look like? Okay, let's say we are passing in width of 224 into the image. We have width of 224, and we also have the kernel. Don't forget, we said the kernel size is 3. And we are using a pattern of 2, or a pattern of 1. So divided by the stride of 1. Plus 1. See, we are still getting our 224. So if you are not using padding at all, like this will be 0. That will be 222. So now for the pooling layer, is also similar to this function. In the pooling layer, we are getting what, 112 by 112. So how does that work? We use this 224. It's taking the 224 feature map from the ConvNet, and we are using a pooling a kernel size of 2 to 2 divided by a stride of 2. So we use plus 1. So you see we have 112, and if we check the shape, the output shape here is 112. So that is the ConvNet output. So I hope we've been able to get the basic intuition of how ConvNet works. how um, how to train them and how to use transfer learning. So that is the basics. So if we can understand what covenant works, so this same principles, this same ideology is used for object detection, for image classification, and for all other things that involve images. So to go further, for useful link, I will recommend practical deep learning for coders, and you can also check out CS2T1 in convolutional neural networks for for visual recognition. So these classes are good. First year, as it comes with the practical aspect first, then move to the theoretical aspect to get a more solid foundation in it. So thank you for tuning in, um, and I hope you further the study of deep learning by visiting um, those those courses, the Fast AI and the CS231. So thank you. Have a nice day.